Alright everyone, so for our second video of the week we want to talk about another application of derivatives. And this one will be what's called the mean value theorem. So before we get there, we want to give one introductory result which is known as Rolle's theorem. So with Rolle's theorem, if you give me some continuous function over a closed interval a to b that is also differentiable in between a and b, and also the two endpoints are the same, so f of a is f of b, then we're guaranteed to have some point c in the middle so that the derivative at c is 0. Okay, so one illustration of this. So suppose that we want to find an interval so that Rolle's theorem applies for the function x cubed minus 7x squared plus 10x. So in other words, what we want to do is find 2 points so that f evaluates to the same thing at these 2 points. So the easiest way of doing this is finding a place where the function evaluates to 0. So if we go and we factor our function, we can factor it as x times x minus 5 times x minus 2, and that tells us that f will evaluate to 0 at all of 0, 2, and 5. So if we pick any of the intervals 0 to 2, 0 to 5, or 2 to 5, Rolle's theorem will apply. So at the for any of those three intervals, we know that f will be continuous everywhere, so it'll be continuous on whatever closed interval we pick. It'll be differentiable anywhere, so it'll be differentiable on the inside of any interval we pick. And we've now got 2 points where the function evaluates to the same things at the endpoints. So we're guaranteed to have some point in the middle so that the derivative is 0. So let's just see what this looks like pictorially. So we could go and take the interval from 0 to 2, and what we see is that in between, here around 1, there's a place where the derivative is 0. But also, if we went and took the interval from 2 to 5, there's also this point around 3 3/4 or so, where the derivative is 0, and then clearly if we took the interval 0 to 5, we had the points on the inside where the derivative was equal to 0. Okay, so how does that help us? Well, so then there's this really handy result called the mean value theorem. So this one says that if you give me a continuous function on a closed interval from a to b, and it's differentiable on the inside of that interval, then there's going to be some point in the middle, which we'll call c, so that f prime at c is equal to f of b minus f of a all over b minus a. And the way you would go about showing this, if you were really interested, is you would just go and reduce this down to a Rolle's theorem case and then solve from there. The textbook would have the proof for this result in the section on the mean value theorem, but it's not something that we really need to go over because it's not going to show up on tests. But to put this into, say, non-mathematical words, or to simplify this maybe a little bit, what the mean value theorem says is that if you give me a continuous and differentiable function on some interval, then there's some point in the middle of that interval, somewhere in between the two endpoints, so the instantaneous rate of change at that point is equal to the average rate of change over that interval. Or in other words, there is a point that if we were to find the slope of the tangent line at that place, the tangent line would be parallel to the secant line connecting the two endpoints, and we'll see this with a couple of pictures for the examples. So 2 examples of this. So let's suppose that we have f of x is equal to the square root of x, and we're looking over the closed interval 0 to 1. Well, we could find that f prime is equal to 1 over 2 times the square root of x. And then we just want to find the points c that is guaranteed to exist by the mean value theorem. It's possible we have more than 1, but we're guaranteed to have at least 1, because the square root of x is continuous on the closed intervals 0 to 1. Remember that we'd said for closed intervals and continuity at the left endpoint, your function just needs to be right continuous, which the square root is. It's not continuous on both sides because if we went over to the negative side, the function wouldn't be defined. And then for differentiability, square root of x is differentiable at all positives, and the inside of our interval is going to just be containing positives. Okay, so we're guaranteed that we have continuity and differentiability. Now we just want to find the point C that we're interested in. So we'll go and take our derivative, evaluate it at some mystery point C, and solve that equation equal to the slope of the secant line connecting the endpoints. So the slope of our secant line connecting the endpoints, so f of 1 minus f of 0, all divided by 1 minus 0. Or in other words, we have 1 over 2 times the square root of c is equal to 1. We can go and simplify things down a little bit and get the square root of c is equal to 1/2, or in other words, c is equal to 1/4. And if we go and we plot a picture of this, what we see is that at the point 1/4, the tangent line to square root of x is parallel to the secant line that connects the points 0, 0 and 1, 1, which is what's guaranteed to exist by the mean value theorem. Okay, so for the second example, we're going to take the polynomial x cubed minus 3x plus 1, and we're going to look over the interval minus 2 to 2. Because we're dealing with a polynomial, it's continuous and differentiable everywhere, so we have the two conditions we want from the mean value theorem. Now we just need to find the point C, or possibly multiple points, that are guaranteed to exist. So we go and we find our derivative, we get 3x squared minus 3. We'll go and evaluate that at some point C, so we get 3c squared minus 3, and we'll set that equal to the slope of the secant line connecting the endpoints, so the values where x is minus 2 and then also 2. So we get f of 2 minus f of minus 2, all divided by 2 minus minus 2, and expanding things out, we get that the right side of that expression is going to be 1. So adding the 3 to both sides, we get that 3c squared equals 4, and solving for c, we get that c is equal to plus or minus 2 over the square root of 3. So we get 2 points that will satisfy the mean value theorem in this case. One is positive 2 over the square root of 3, the other one is minus 2 over the square root of 3. Again, we have pictures for these, so we have the polynomial x cubed minus 3x plus 1 in blue. We have the slope of the secant line connecting the endpoints at minus 2 and 2. And then we have these two tangent lines, so one at plus the square root of, or plus 2 over square root of 3, and minus 2 over square root of 3. And what we see is that the tangent lines in these cases at 2 over square root of 3 and minus 2 over square root of 3 are both parallel to the secant line that connects the endpoints, which is again what we're guaranteed to have by mean value theorem. Okay, so then one important case to also look at is why the conditions are important. So the mean value theorem requires that you have a function that is both continuous and differentiable for the conclusion to hold. So the existence of some point that has instantaneous rate of change equal to that of the average rate of change. And the same also for, I guess, Rawls' theorem. So for this case, what we have is just a plot of the absolute value function. And what we see is that the function at the endpoints here, so we're looking at minus 1 and 1, the function evaluates to the same thing. It evaluates to 1 at both 1 and minus 1. So if we naively went ahead and just forgot to check our conditions, what we would expect is to have some point in between minus 1 and 1, so that the slope of the tangent line at that place was 0. But what we know is that the absolute value function is going to give slopes of minus 1 for all the negatives, slopes of 1 for all of the positives, and an undefined derivative at 0. So there is no point in between minus 1 and 1 where the slope of the tangent line would be equal to the slope of the secant line connecting the endpoints, in this case 0. So again, so this says that whenever you're doing these kind of problems, just make sure that you check for the continuity and differentiability. Okay, and then the last thing that we want to say on this topic is just a couple of implications. So suppose that we have a function that is differentiable, And we're also told that the derivative is equal to 0 everywhere on some interval I, then that's going to force our function to be a constant. Now, why might this be? Well, suppose that we have 2 points A and B that are in this interval. Then we would know from the mean value theorem that the slope of the secant line connecting these points A and B is equal to f prime of c for some point in between. But because we've said the derivative is 0 everywhere, that says that the slope of the secant line has to be 0. But what we could do is multiply both sides by b minus a. We're assuming that a and b are 2 different points, so b minus a will be something non-zero. That says that f of b minus f of a is equal to 0 everywhere on this interval, or f of a is f of b. But because we made no assumptions about a and b, this result is going to be true for every pair of points in between in our interval I. So this says that the function f has to be constant on the entire interval I. Okay, so and then the second implication is kind of related. So if you give me two functions that have the same derivative over some interval, then they have to differ by a constant. And the idea with this one is to define some other function h equal to f minus g. But then if we only take the derivative of that, we get that h prime is equal to f prime minus g prime. And by assumption, we've said that that is 0. So from the previous result, that says that h has to be equal to a constant, or in other words, f minus g is equal to a constant. So f and g just differ by a constant. And this is something that we're going to come back to in about a week. And we'll just mention this again, because it's important when trying to undo derivatives. Okay, so I think that's about all that needs to be said about the mean value theorem. I will have some potential quiz questions up over this topic and the previous one, and then as before, we'll have another quiz on Friday. If you have any questions, please don't hesitate to send me an email. All right, bye.